And we're back. In this segment, I'd like to talk about a consequence of how we defined the momentum of a system. He said that the momentum of the system was the sum of all the things numbered 1 to n. I think I used index k. Let k run from 1 all the way to n, however many things there are. And I keep drawing a thing that looks like a U there. N of the individual momenta of the n components added up like vectors. Okay. I'm going to stop with the indexing and whatever. I'm just going to end up writing m for each one, for each k equals 1, 2, 3, all the way up to n. The momentum of the kth one is its mass times its velocity. Suppose we multiply both sides of the equation by dt. There's actually n terms in this sum, but we can multiply through a sum, right? We can just multiply dt to every term, so I really don't need these parentheses. Each of the n things, find its mass, find its velocity, multiply by dt. We could integrate. Integrate sum of m k v k t. Okay, now the integral is itself a sum, and in each of the terms, m is constant, right? Whichever, k equals 12, the kth mass is what it is. It's a constant number. So its integral, we can pull outside each of the terms for each of the 1 through n pieces has a mass, a velocity dt. If we pull the mass outside that term's integral, we're just integrating v dt. So for each one, we're going to end up with a mass times the integral v dt, and we're going to have n of those because there are n pieces in our system. Let's integrate from 0 up to capital T. So it's a definite integral. We got to plug in t, we got to plug in 0, but the antiderivative of velocity is position. So what each of the n things, we multiply the mass with R at capital T minus R at 0. Which looks to me like T minus whole summation that we're going to get two terms for each of the n things, one for the product of the mass and position at time t, and one for the product of the mass and the position at time 0. Okay, great. So far, I've left the left-hand side of this equals the left-hand side of this equation. I've left it alone. But well, if the system has some momentum, then presumably, according to our definition of momentum, the system has some mass and some velocity. That's how we define momentum. If the system has momentum, then I guess it has kind of like at least an effective mass and an effective velocity. From this line to this line, we multiplied by dt, so I'll just bring everything else down. M system, V system, and then in the next line, we integrate it. We're going to end up integrating M system integral from 0 to t, V system, t. But this is going to get us M system R of t system minus R of t, or I'm sorry, R of 0 system. M system T, oh wow, we're getting all kinds of stuff here. M R system minus space. Hold on, I got it back. First term M system R system of T minus M system R system at 0. In order for this equal sign to still work, if we change the value of capital T, this term changes. This one stays the same. This one changes. That one stays the same. So the only change we can get in the left-hand side is from this term. And the only change we can get on the right-hand side is from this term. So I think these two terms are linked changing this one changes that one. Always. Changing this one will never change this one. I am system or system at T appears to be doing the same job as this term. M sub K R sub K. Because this term isn't changing, and neither is this one. And if we're going to keep this equal sign preserved, this one and this one need to be tied together. That's the only way we can get capital T components from changing one side to changing the other. This is the only way to ensure that whatever we do to this one will always be the same on this side. We've been talking about the position of the system, that that the system as a whole, in components, lives at one position in space, this position. Where is that? That's the part. Like, all right, we've talked about the system's momentum, which means its mass and velocity. And if we're talking about its velocity, that means we're talking about its position, because that's what velocity is. It's the rate of change of position. So, all right, so there must be somewhere that the system lives. How do we know where that is? It's this deal in purple. That's the piece that tells us where the system is. Our system is apparently, as a function of time, I mean, call it T, whatever you want, lowercase, capital, doesn't really matter, is the sum for all the n pieces of the system and then we've got to divide by mass of the system, which I think is exactly what it sounds like, the total mass of the system. And that means that this is a sum of all the masses. And that means that this expression is a mass-weighted average position. Each position, we multiply by how much mass lives at that position, and then we divide the sum by the total amount of weighting in the average, the total mass that we have present on average. At what position is it? The position of the system. Center of mass. Where is the average center? It's at the mass-weighted position average. Cool. What if n is arbitrarily large? What if this is a a real-sized object with I don't know, God knows how many individual masses, uncountable, right? Molecules, individual molecules, or it's a continuous object. How many little masses are there? How big are they? I mean, they're tiny, right? So what if n goes infinite and each little mass is very, very, very small, infinitesimal? The sum of a whole bunch, infinitely many, infinitesimal pieces, that's an integral. Where the integral here is over the entire system. You'll practice this calculation in the discrete and the continuous cases in mastering physics. But this isn't really its own definition. It came from here. It's a very natural thing to say that the total momentum of the system is the combination of the momenta of its pieces, which is another way to say that the system lives at the mass average position of all the constituents of that system. One of our worksheets this week will explore some applications of this idea. The story now that we have this center of mass idea, is that we can rewrite Newton's second law. The sum of the force on the external force on a system is the mass of the system times the acceleration of the position that is the acceleration of the system entire, the acceleration of the center of mass of the system. Forces external to the system. And that speaks to the internal-external idea that we were talking about in the last segment. So a system behaves according to the net force on it. Just like an object would, right? If we throw an object, it behaves according to the net force on it. A system does the same thing. As long as the forces that move the pieces around within the system are in fact internal to the system, then the system at large has to behave like any other object subject to these external forces. Interesting. Okay. Next segment.